Hello, this is the final activity for our DSP class. This is a compilation of all our activities from Laboratory Experiment 1 to 16. In this video, I will cover the first half of the said experiments from 1 to 8. In number 1, we are tasked to find an 8-point DFT of the sequence given 1, 2, 3, 4, 4, 3, 2, 1. In the first diagram, we can see the amplitudes of our values and the time index. So here at time index 0, we enter the 1, an amplitude of 1, which corresponds to this. Then we see 2, 3, and 4, which corresponds to time index 1, 2, and 3. This point to this point to this point. Then we go back down 4, 3, 2, 1 from time index 4 to time index 7. These are those points. Then for number 2, we are tasked to find the linear convolution given x of n with an array of 7, 5, 4, 0. And the second sequence of 0, 3, 6, 2, 9. So in the first diagram, we can see here the inputted first sequence that starts at 7. The second will be at 5 here. Then 4. Then the last one is at 0. The second diagram corresponds to the second sequence that we entered, which starts at 0 and valued in the second one at 3, 6, 2, and 9. And the last diagram represents the values of yn. And here we can see the values are 0, 21, 57, 56, 97, 53, 36, and 0. And here we can see the first value is at 0, the second is at 21, the third is at 57, the fourth at 56, here at 97, 53, 36, and back to 0. So in number 3, we are tasked to find the autocorrelation function of a ramp sequence for 0 less than or equal to n less than or equal to 6. So our input sequence will range from 0 to 6. In the first figure, we can see our input sequence, and on the second one, the autocorrelation input sequence, which are given as the values of z. In here, we can notice a exponentially increasing value which peaks at 91, then it decreases at the same amount till it returns back to 0. And on the second diagram, we can see that the points exponentially increases until it reaches a peak at 91. Then the curve goes down, the point goes down, equal to the first half of the curve. Here we can see that the point is at 70. That for number 4, we are asked to find the frequency response of the system described by the difference equation y of n minus 3/4 y of n minus 1 plus 1/8 y of n minus 3 is equals to x of n plus 2x of n minus 1. So to do this, we must first turn the given equation into a fraction. So our numerators would become x of n plus 2x of n minus 1. Our denominator will be y of n minus 3/4 y of n minus 1 plus 1/8 y n of n minus 3. So our numerators are 1 and 2. These are the coefficients. And the denominators, the coefficient of the denominator are 1, negative 3/4, and 1/8. In here we can see two figures. The first one is the magnitude response of our given equation. The second is the phase response. At first glance, we can see that the curve is almost identical. But upon closer inspection, we can see that the magnitude in dB in magnitude response has a slight curve before exponentially going down. But in the phase response, we can see that the values of phase in radians immediately go down. Then it has a slight curve before going down immediately again. Next one is number 5. Is to find an 8-point DFT of sequence x of n is equals to 1 2 1 2 3 4 4 3 using FFT algorithm. So FFT is fast Fourier transform. So here we enter the given sequence, which is 1 2 1 2 3. So in here we can see here in the first graph, we can see the input sequence that is given to us. So in magnitude response, we can see that the values here correspond with the values given at xk. Here. And the IFFT, the values are given by the variable xn. So next one, for number 6, we are to find the power spectrum of a signal x of n is equals to cosine of 2 pi times 50 times n. So the equation of the signal is already inputted by the code. So to check, we can see here the lab 6, and here we are and here is the equation, the cosine 2 times pi times 50 times n. So here we can go back to the figure displayed by the program. So here we can see that the magnitude of the power spectrum exponentially goes down as the frequency goes higher. The magnitude is in decibels. So for number 7, we are to design a low-pass FIR filter using Bartlett and Hamming window. So for the Bartlett, so here we can see the low-pass FIR filter of the Bartlett window. We can see that the magnitude response of the low-pass filter exponentially goes down before it starts to stabilize at the later half. The phase response has an even distribution of in angle and in frequency. For the Hamming window, here we can see that the magnitude response of the low-pass filter using Hamming window has the same value from 0 to 0.2, then it exponentially decreases, then stabilizes it again at 0. For the phase response, we can see a more erratic frequency at the later half, and the angle and the amplitude of the angle has slightly decreased. So to better compare Bartlett and Hamming window, we can see here on the left is the Bartlett low pass filter, on the right is the Hamming low pass filter. in the Hamming low pass filter, we can see that the gain in dB from 0 to 0.2 is equal to 1, but in Bartlett low pass filter, we can see that it is slightly decreasing before it exponentially decreases from 0.2 to 0.5. Then it decreases slightly from 0.5 to 1. But in Hamming window, we can see that at somewhere between 0.5 and 0.6, the value in gain in dB is equal to 0. For the phase response, we can see that the Bartlett low pass filter has a more stable phase response compared to the phase response of the Hamming low pass filter. So for number 8, we are tasked to design a high pass FIR filter using rectangular and Hamming window. So to display a rectangular, you can use the boxcar code, and for the Hamming window, we can use the command Hamming. So this is for rectangular. The magnitude response of a high pass filter, sorry for the typo, we can see that the values of the gain in dB from 0 to 0.5 is slightly increasing and decreasing, but it exponentially increased between 0.5 and 0.6 before dipping slightly and back up again from 0.7 to 1. For the phase response, we can see a smaller angle from 0 to 0.5, then it increases from 0.5 to 1, but it has the same frequency. So let's check for the Hamming window. Here in the Hamming window, we can see that the value of 0, the value of the gain in dB from 0 to 0.4, in between 0.4 and 0.5, the gain in dB is equal to 0. Then it exponentially increases, and at somewhere between 0.7 and 0.8, it normalizes again at gain in dB equals to 1. For the phase response, we can see a more erratic behavior. The angle exponentially increases, then stabilizes again between 2 to 4 and negative 2 and 4. But we can also observe a more erratic frequency of the signal as it travels to the x-axis. So a side-by-side comparison of the two. On the left, you can see the rectangular high-pass filter, and on the right is the Hamming high-pass filter. Here we can notice that the magnitude response of the rectangular has a more erratic behavior compared to the Hamming high-pass filter, which has a smoother curve. But we can see that the phase response of the Hamming has a more erratic behavior compared to rectangular high-pass filter. Thank you.